those of you who do not know, I am Michael Morgan.
And I never have been. And I'm Mr. Larson.
As best any of us can recollect, this is the 16th one of these that we have done, okay? It might actually be a little bit longer, okay, in a row at least. Throw in a few more that were out of order, and this is about the 20th time that we have done this. Now, our name today, Faraday Lecture, comes from a historic scenario, and that is in the early 1800s, Michael Faraday, after having apprenticed as a bookbinder, okay, self-taught physicist, chemist, etc., becomes head of the Royal Institution. And he comes up with a very interesting and novel idea. A week-long series of lectures, 2 hours a day, for the week leading up to Christmas. And this is in London, a place where parents can bring the kids because they are out of school, okay, and they can actually learn something, okay, in a nice controlled environment. Now he had a theme.
Well, wait a minute, and they're away from parents while parents are Christmas shopping,
Yeah.
so it's a place to park the kids.
Child care. That's it.
For free.
For free.
Yes.
1 year, his theme was the chemical history of a candle. This is a guy who spoke for 10 hours about candles, and the kids actually paid attention to it. Okay, understand that. A very different scenario. I go for 10 minutes, and y'all are just off into bozo. Okay? He published that series that year. Okay, there you can find the book. It is in Bravo's library. We have 2 copies. A Chemical History of a Candle. So, because of that, we always start this out with one specific demo. And then we go in some different directions. Okay? If you were here last year, you're going to see a lot of very different this year. Okay? We have a couple of old favorites we promise we won't ever completely surrender on. Okay? But we do try to change it up a little bit. So I'm going to start this out before I get into the theme for this year too much, with this. Now what we have is a bucket of dry ice, okay? It is neither dry, nor is it ice. First off, to be ice, what would it have to be made of? Water, and this is not made of water. This is made of carbon dioxide. And while it does not melt, it sublimes directly. Okay, it isn't. We got some right over here for you. Oh, thank you. Front and center if you want. Yeah, you have the splash zone if you want, or a comfortable chair for you. You
You want to sit over here?
This is good.
Now,
It's close enough.
I can't let you completely get off the hook, so I got to ask you a question. What's holding the CO2 molecules to other CO2 molecules in there? What's the intermolecular force?
Ironic binding. English teacher.
It's one of the van der Waals. Van der Waals is the old name for it. Now we would call it a London dispersion force. Okay, because now we actually differentiate between London forces and dipole-dipoles, which van der Waals did. But those are weak forces, aren't they? So when I drop a couple pieces of dry ice into here, what's it going to do? No, it's not going to melt. It's going to sublime, and it's not going to evaporate. Okay, we have to be careful. Words have meaning, don't they? Sublime, it's going to go from the solid to the gas. Now what's going to happen is we're going to fill this aquarium with carbon dioxide. And these flames, okay, as you can already see on the purple one right there, what's going to happen to these flames? They're going to get suffocated. They're going to get snuffed out. Now, when I was in school, and this was a very different time. We were taught a technique called pithing. Okay? They gave us our frog in biology, and Kermit was still Kermiting. Okay? And we took a pair of scissors, and we didn't cut it open. We took the top, back of the head off. Okay? And then we dissected them. Okay? Lisa, you dissect critters, little furry things. Okay? You don't pith them anymore, do you?
Thankfully, we don't do that.
You put them in one of these, don't you? A couple of chips of dry ice, go to lunch. Come back, and they have gone to sleep. Okay? We're going to let this go for a few minutes. You're going to see them go out in order while we talk about some themes. Last year was the International Year of Chemistry. It was all chem. This year, our theme is kind of been governed by some of the losses that we've had this year. And those of you that have been here before us, I tried to put up some notes about some people, okay, that have left us during the year, okay? And there's two names that really, really dominate this year. One of them is Neil Armstrong, okay? And we were trying to talk about, what should we write up on the board about Neil Armstrong? And, simplest thing, first man on the moon. And Larry was like, why are you writing anything? If you don't know that name, okay, we want that nerdy shirt back.
Leave now.
Yeah, get out. You are not a geek. Okay. And Sally Ride. Okay. Sally Ride was not the first woman in space, but she was the first American woman in space, and the first one to actually get up to a decent height orbit. Okay. Valentina Tereshkova, it's Masha here. Just tell me if I'm saying that right. Okay. Was the first woman to actually get up into space. Okay? So, we thought we'd talk a lot about physics and space stuff. And we also have curiosity. Okay? We've had one of the most important landings you can imagine. We've got a real lab sitting up there on the surface of Mars. So we're going to show you some of what they're doing. Now, coming back to this. You ever heard of Apollo 13? Okay, they had a problem. Houston, we have a problem. All right? And they needed a lifeboat. And it's kind of hard to have a lifeboat when you are going at 17,000 kilometers per hour, or miles per hour.
But faster because they left Earth orbit.
At that.
That's the speed to orbit the Earth, and they go faster in a way.
They're going fast in that. They're heading to the moon. And all of a sudden, they have to get into a LEM, a lunar excursion module, which is designed for 2 people for 2 days. And they put 3 people in it for 5 days. And they're breathing. And the oxygen in is good. The carbon dioxide out, it's good. When it comes out, it's bad when it builds up inside of that capsule. Okay, and leave it to the government. The carbon dioxide scrubbers on the Saturn V were circular.
In the command module.
On the command module, they're circular. And in the LEM, they were square. How do you build an adapter when you're up in space? By the way, duct tape was involved. Understand that? And a sock, believe it or not. Okay? So that carbon dioxide, they don't want it building up in the capsule, because what's going to happen to our astronauts? The same thing that happened to Lisa's rat. Okay? They can go nighty-night. Okay? I'm going to let this go for a few minutes. There's a few other people up here you see we're talking about. Nothing with space up, Endeavor. Did you miss that over the summer? Okay? It's come to Los Angeles. Okay? And I'm sorry, but I'm a Sesame Street guy. Jerry Nelson. Okay? He's the reason I got through math. Mr. Quippy.
All right. So, I don't know quite how this fits in, but this next demo, it involves water. Actual, not dry ice, but actual liquid H2O. And what I have here is just, as you can see, nothing surprising. It's just a bottle here, and with water in it, and some air at the top. I'm going to light a match because I want a little bit of particles, a little bit of smoke in there. Yes. Clap. and see how it looks, and I let go, oh, and now I have a cloud in the bottom. But I don't want the cloud, so I squeeze it, goes away now. I got a cloud now. This might help you see it. If you dim some of the lights, maybe not the cloud. So can you see the green beams? Yeah. Cloud. Gone. On, off, you know, just turn the cloud on and off. No, okay. No. Now.
Not sure I want him handling my life support.
Does that work? You said very well. Why does that work? How do I? And work is a key word there. What do you need to have a cloud happen? Water vapor. Yeah, that's why there was water in here. Something to attach to it. That's why the smoke was in there. So you have little particles in the air. So you have condensation nuclei. Vocabulary words. And what else?
Pressure.
No, it's not the pressure.
No?
No. It's the temperature. How am I changing the temperature by squeezing it? You hear about the dew point? Okay, well, yeah, it's less point. So if I squeeze it, I compress it, right? Okay, I've done work. I've lifted that water up. I've compressed that. I put energy in. When I let go, why does it go back down?
Shall we make fun of the French?
Okay.
Gay-Lussac. Joseph Gay-Lussac.
Oh, it doesn't go back down now. Why not?
Somebody over here said not enough pressure.
Yeah, none of there, yeah. So when what makes this go back down when I compress it and let go? Why does it go back down? It's the air pushing the water back down and pushing the size of the bottle out. The air has to do work. And what does it take to do work? Energy. So the air lost energy. So now it's below the dew point, and you get a cloud in a bottle.
Rockets need to maneuver in space, don't they? Now, for every pound that you want to lift off the ground, how many pounds of propellant do you need? You're a little high. It's 3. 3 pounds of fuel for every pound you want to lift. Okay? And this is a rocket with a whole lot of liquid hydrogen, liquid oxygen, hydrazine, and dinitrogen tetroxide. They are hypergonic. You put those two together, they react. You don't need to do anything else. No activation energy hump to get over. It just happens. This is dangerous. Okay? So you don't want to take a whole lot of that if you can avoid it. So when you're up there and you want to maneuver, it's not quite as hard as maneuvering an airplane, because when you turn a rocket, there's no wind resistance, is there?
Okay. When there's no wind.
Not when there's no air up there. So they came up with a novel approach to how to do it. And it's based on a simple old magic trick, chemical demonstration we have called Genie in a Bottle. Okay. The bottle's covered, you can't see in. What I have inside the bottle at the bottom is some 35% hydrogen peroxide. Now, this is my brown bottle of peroxide. I have a brown bottle of peroxide at home under the sink. It's not the same. First off, it's not an accordion bottle. Okay, because there's not that much decomposition. Although when you open it the first time, you hear the fizz. Okay, that's 3% peroxide at home. This is 35. Yowza. It will bleach your hair, however. It turns blonde about the time it hits the floor. It happens that fast. Okay? Now, I'm going to decompose it with the catalyst. So the magic trick part is that when I pull out the cork, there is a string right here. And I have a tea bag in there that we emptied out. Okay? and we stuffed it with some potassium iodide, which is a good catalyst for decomposition. H2O2 breaks down into H2O and O2. The liquid becomes a gas, actually two gases. The water comes out as water vapor. Gas under pressure. I can use that as a rocket. I can use that to maneuver, and I don't need a whole lot of it up there in outer space. You do realize you're in a splash zone, right? Remember those Gallagher shows from the 80s when they put sheets of plastic down in the front row? They could hold them up. We got to do that sometime.
Or you could use a shield that's right there.
That's all right. Front row makes good shield.
Front row shields the second row, is that what?
3, 2, and 1.
Oh, just kidding.
Xander, I think we used too much. Some of you will remember that line from Real Cheese with the popcorn. Okay, now, they do that inside one of those rockets, literally, on capsule, okay? All that pressure builds up and they can release it when they want to. That got stuck open, that valve, on a Gemini mission. And they had no idea. You had Dave Scott and Neil Armstrong in one capsule, and you had a Gina unmanned rocket on the other end, and it started to spin.
You know, I think.
Let's go for it.
Order, but
Okay. And man, Neil Armstrong sealed his fate as the first man to walk on the moon that day because he got that capsule out of that roll and brought it back to Earth. You got to realize this guy was a Navy fighter pilot and test pilot, and that's what they needed for those astronauts.
So you start something spinning and something interesting happens. Notice I'm spinning the wheel one way, but what's happening to me? Yeah. See, there's this thing called conservation of angular momentum. So I'm standing on the ground now to get this spinning up without me going around the opposite direction. Do you notice how helicopters always have two? Because if you have one spinning one way, you have the other spinning the opposite way and it cancels out. What happens if you only have one spinning? And oh, the gyroscope effect. Speaking of spaceflight, this one way you control attitude of satellites. You just put a little torque on the gyroscope and you can position them and turn them. All right. Now, the other thing that happens, conservation of angular momentum. I didn't know you would tell this Kojima story, but
Neither did I.
one of the problems they had was they thought, okay, there's something wrong with, they were just docked, and this problem started when they just docked with the Aegina, and it started happening up. And so they thought one way to get rid of the problem was undock, right? Because the problem might have been with the Aegina thing they were docked with.
And an Aegina is bigger than a Gemini capsule.
And so it's more massive, so let's see if I can do this. And then the more mass, you pull the mass in, you get smaller mass, and you spin faster. Because there's less mass. And the problem was with the jet on the capsule. And so when they undocked, they had less mass, less inertia, and they spun up faster and faster.
Accelerating.
Yeah. Going faster and faster and stuck like that. Now, have you ever been on the teacups at Disneyland? Imagine them going faster and faster and faster and faster. And now think quick and how to fix it.
Okay. Now, interesting unintended consequence here. You've been watching me. Have I been fiddling with that bottle? No. That's tea bag. Did I just pull it out of the bottle? No. it came out of the bottle on its own. It was shot up, okay, by that buildup of pressure. Okay, wasn't intending for that to happen. That's kind of cool. Yeah, oh, you were? You put a lot of iodine in there? Oh, yeah. Okay. Yeah, you know, jump around all we want. Okay. Actually, let's take a look down here. How are these guys doing?
They're slowly dying.
Slowly. We got 2 down. Okay. More to go. All right. Go for it. Standard.
Places. Now, what I've got here is lasers. Now, you know light travels in straight lines, right? In fact, that's usually how we define a straight line. You want to know if something is straight, you put your eyeball next to it, and you see if it's straight by comparing it with a ray of light that comes along this way to your eye. So that's how you know if it's straight or not, right? Light travels in straight lines. So I'm going to shine this laser at this guy right here. And what's in here is water. And literally, there's a hole in it right here. An open hole. There's no plug in it. So, yeah. Why is the water not coming out of the open hole? Because the top is on, so the air is not pushing the water out. Now, you want to try some fun, and in a place where it's okay to make a mess, take a bottle like this, with here, put the finger over here, stand up and jump off, and when you jump off, let go, and watch the bottle come down. The water won't come out. As long as the bottle is falling, it doesn't matter how many holes it's in if the water doesn't come out. Yeah. All right.
You guys got to play in the backyard. I'm not joking.
I used to take buckets of water. Until you stop.
Okay.
Okay, Stanley, can I get you guys to squeeze over with Jody?
Yeah, because we're shining laser light, and it should be coming out, yeah, straight on through, and it should be coming out that open hole. If I line it up, skew it a little bit, should be okay, Mike. Should be. It's looking straight like a go. Alright, so straight on through here, and if we could have the lights off, if I can do this now, moving, yeah.
We did this one year, and it took Patrick 8 hours. It happens to me in the middle of the night. If you say close, on occasion. Oh, damn! You kept the light in it.
See what you do is, it's called total internal reflection. Light going in and bouncing on, you've heard of fiber optics? That's the way fiber optics work. You shine light down the fiber and it bounces off the walls and stays inside. It can't come out. If I were to get some clear up, you know, places in the water that doesn't have, you want to know the trick? What's the trick?
There's no food coloring in there.
No, there's no food coloring in there.
Oh, come on. Don't you remember titration?
Phenolphthalein.
Yeah.
No. Phenolphthalein and a little bit of base.
So that's just the red laser. You all thought I trapped the light down
Okay. Now, this is a stretch for space program, but it's just kind of cool anyways. Okay. Imagine what it must have been like to be working in the control room at Kennedy, okay, while they were trying to land people on the moon, especially for that first time. These guys must have been smoking like mad, okay, and living on stomach medicine. So what I'm going to do is just put a gallon of distilled water in here, nice big flask. You've heard of microscale chemistry. Well, this is microscale chemistry. Okay. Now, milk of magnesia. Okay. This is the plain rap stuff because I'm cheap. Okay. The brand name is that Phillips? That's Phillips. Okay. Shake it up real good. Now, like most medicines, ignore the label, just pour into whatever cup they gave you. Okay. You know, I want to mix this. So I think I'm going to take a little magnet here, drop the magnet in, and turn on an electromagnet beneath it. Okay, that's the way to stir things in the kitchen. Never do anything by hand that a machine can do for you. KitchenAid. I've got 2 of those.
I didn't know you guys knew how to cook.
Okay. Time for reactions quiz. Ready? Okay. Solubility of magnesium ion and hydroxide ion. Not soluble is not correct. Sparingly soluble or in water. Slightly soluble. So I've got this going here. Okay, I've got it mixed up, but it's a little cloudy, isn't it? Now magnesium hydroxide, basic or acidic?
Basic.
Basic. Okay, little universal, probably good. A universal indicator. Now indicator, especially universal in general, the blue colors tend, but not always, to be over on the basic side, and the red tend, but not always, to be over on the acidic side. So I got some stomach acid here, so to speak. A little vinegar. Now, let's give it a dose. Okay, now, we're seeing the red, aren't we? Except milk of magnesia is a nice buffering agent. What's happening is it is currently consuming that acid. The H pluses are getting used up by the hydroxides. It doesn't happen instantly, okay, because the magnesium, old name for it, is not totally soluble. So it's happening slowly, and what is happening to that color? It's going back, isn't it? Okay, it's getting lighter, it's shifting back towards the basic side. So you go out and you slam a couple of Big Macs. Okay, actually, it's probably going to be the what's the new one, the pork one they just brought back? McRib. Okay, it's back. And if you buy the combo, you get a second sandwich for only $1. So you slam a couple of those, a little too much stomach acid gets produced, you get the upset tummy, you take a dose of this, and it consumes a lot of that extra stomach acid and starts to buffer. Okay, gets you back to a more comfortable tummy pH. Now, since the extra sandwich is only $1, you can supersize your eyes.
Oh, you're getting serious about that.
And the big Coca-Cola.
And lots of mayonnaise in there with some acid.
Yeah, it's all diet. Now, you see the red. But you know what else I see? I see CJ. Literally. I can start to see through this now, can't I? Which means
Water's being
water's what?
formed by when the hydroxides come out of the hydrogen.
No, but thank you for playing.
You're using up the magnesium?
It ain't making up that. I've used up all the
Magnesium?
magnesium hydroxide. It's not in solution anymore. The soluble is taken over for the insoluble. It's not going to go back this time, is it? Okay, I've burned up its buffering ability. Buffers have a certain capacity. They don't buffer forever. Okay, and when they're done, they are done. Mr. Quimby.
Yes. Have any of you miscreants ever tried playing a BB gun or yeah. So something is hard to, I mean, some of you just shoot basketball, right? And so that's basically a projectile, and you got a target when you get there. And you think that's challenging enough, right? And well, we mentioned the teacups at Disneyland. Imagine trying to do your projectile launching while on the teacups at Disneyland and trying to hit somebody standing aside. That would make things challenging, right? Now imagine your target was also moving. So you're on the teacups, you're spinning around like this, and then the target's also moving.
You know how NASA described it? You stand in the backyard, I'll stand in the front yard, and we'll throw rocks at each other over the house. And we want those rocks to hit each other above the house when we can't see where the other guy's throwing from. How hard is that? Kind of hard.
So, fortunately, Newton figured out a whole bunch of this stuff prior to NASA needing it figured out. And there's some actually pretty ridiculously simple equations that'll let you calculate it. But well, you guys need to be holding on talking because you have to do this after the setup. But there are some conceptual interesting things. Oh, darn. Okay. What I've got here is a little projectile launcher that's been hidden by the Van Graph generator. We got too much stuff. And the projectile I'm going to use is just a piece of dowel that fits in this tube here. You can see some wires here. Now the other end over here, they're setting up the target. I hope. Yeah. You got
That polar bear was a gift from Kim Tran, class of '94. And it's still here. And if you notice, you know Morgan well, she added something to the Coca-Cola can.
Now, I gotta talk fast and that thing's gonna overheat, and then this thing has enough trouble working well anyway. Here comes the projectile. This tube, maybe you can see it's in a straight line there. But there's a little wire gap here. When this projectile hits those wires, one, they'll probably detect this and make you miss. But two, it's going to break the circuit, which means the little bear's going to drop. And this is going to demonstrate that when you're aiming a projectile, you shoot it in a straight line. If you aim straight at the target, you're going to miss because your projectile will fall. And it will fall the same amount, the same distance as an object falling from rest.
Did I hear the word parabola back there somewhere?
Yeah, should. Okay, it worked once in rehearsal.
Yeah.
And so that's probably my quota for the decade. There we go. So here. Yep. Yeah. Again. I don't know why that one didn't work. Oh, you want me to try it again?
We'll do a second try. This is the most temperamental physics demonstration there is.
That's why I really didn't want to do it. All right, let me put this back together. All right. The coach at Southgate, he had lung capacity. That thing didn't follow a parabola. It followed pretty much a straight line. Put a dent in my fight board. Damages.
But the bear bounces. It doesn't work.
Yeah, well, okay. That's it. Yay.
It's tough. They did better with the rockets than we did.
Yeah, it's target practice not easy. Oh, go ahead, Uncle.
Yeah.
Just connect the wire.
Some interesting stuff. up there on the Apollo capsules and the Saturn V's, etc. They were trying to keep everything as light as possible, and sometimes some boo-boos occurred because of that. They often used exposed wiring to cut down on the weight of insulation. The problem is they also often pump that capsule full of pure oxygen. And Gus Grissa, Ed White, and Roger Jaffe, you probably remember, it was just before I was, say again?
I read about it.
You read about it. A spark from one of those exposed wires ended up hitting some pure oxygen and incinerating it. So this is a novelty item, okay? It's a light bulb, okay, except there's actually a battery in it. On this post at the bottom, you actually have a blank spot between two sides of it where there's no conductor of any type. So an old style magic trick, and it's magic when we don't tell you how it happens. It's chemistry and physics when we do. Okay. So take a little piece of aluminum foil. Now I've overdone it, big size here. Okay. You stick the aluminum foil on, and what happens is I complete the circuit. You get the light bulb. Anybody ever watch The Addams Family? Uncle Fester?
There you go.
This was it. What he would do is he would take one of these, and he had a little piece of aluminum foil on the end, and stick it in his ear, and it would light up, and then he'd pull it away, and it would go off. So this is kind of our ode to, it's chemistry when we tell you, it's physics when we tell you, it's magic when we, oh, am I still blinking?
Yeah.
Run out my battery. Okay.
So, he thinks that's electricity. Oh, now we have electricity.
Now that's electricity.
Not yet. But this thing's called Windsor's machine. You all that.
Sazi, you don't have anything pierced or any metal on, do you? You know? Okay.
That's my head.
It's okay.
Braces? Belly button pierced? Okay.
Static electricity. Okay, somebody want to hit the lights so we get the full effect of this. All right, crank it up. I hear it sizzling.
He does like bike riding.
So, anybody with a pierced tongue, wanna check this out? All right, turn the lights back on for a little bit. Yeah. Oh. Short circuit. Now, that's a Windsor's machine. Obviously works on static electricity. Many of you with hair are familiar with static electricity.
I remember static years ago.
You have cats, it's the same.
This thing is a Leyden-Jar, dissectable capacitor. Capacitors are used to store electricity. Okay, so what I'm going to do is separate those out so no spark goes there. And I'm not a big fan of electric shocks, by the way, so yeah.
That explains a lot.
Yeah. All right. It also explains why I'm going to come over here and yeah. Right. So now turn this, crank it, and no, where's that? Oh. I can overcharge. What happens if you overcharge a capacitor?
You
get a
replace
nice
the
big
computer in
giant
your car.
spark right through the capacitor, and it's not a capacitor anymore. So now I'm going to stop that and let's see, test it out. Yeah, just so you know. Okay, so now we're going to charge it up again. And then stop. Charge it up again. Stop. Here's the sizzling. It's usually a good sign now. Just you okay? You laugh. You come up. You just
With your braces.
yeah. Shoot. Got me. through the gloves, which is okay. Just not what I wanted to have happen. So, let go. And, all right. Oh, you're laughing now.
Yeah, it's all fun and games for somebody's corpse.
All right. So, all right, hold on to that. Salty, would you please?
I'd rather not. I don't.
There you go. There you go. Now let's touch the ground. It should be grounded, right? Now touch those two together. Go ahead. Touch them together. All right. Now, can I have this back, please? Now that it's all neutralized. And it's, uh-oh. Oh, that's the outside. That helps. Put this back here. And then this. And now, pardon me. I'm still being very careful. And you're probably wondering why, because it's been discharged. Ah, there it is. Really. Sometimes when I've gotten an actual spark about an inch long after all of that. No, well, yeah, we can try again, but what? What's going on? You saw me charge it up.
Simon,
One
please
piece
come
of
to the
metal
main office.
attached here, one piece of metal attached there. They're separated by a plastic insulator. So the two charges, they're charged up equal and opposite charges. One's positive, one's negative. I don't know which is which. Doesn't matter, right? And then I take them apart, we touch the metal together, and I put it back together, and there's still energy, still charged. What's that telling you? That plastic is the key to things. That plastic is where the energy is actually stored. It's the insulated part of the capacitor that's doing the business, which is very interesting when the insulator is a vacuum. So, okay, now we got them all thinking. Quiet. Let's launch the next one.
Okay. I'm making sure we're here. So right now, Curiosity is sitting up there on Mars, and it's got a lab. It's actually scooping up Martian soil, and it is vaporizing it, and it's looking at spectral lines. 410 nanometers, 434 nanometers, 486 nanometers, 656 nanometers. That's the bright line spectrum for hydrogen, right? The Balmer series. And it's able to take pictures of spectra and send them back down so we can figure out what's actually in some of that soil. How is it doing it? Well, if we want to go very old school, it's called a flame test. What I'm going to do is crank this guy up. Alan, if you would turn the lights off. I'm going to start off here with a little bit of copper solution in a squirt gun. Can you see the green? We go this side. Okay. Now, I don't know what the next one was that I picked up because I can't read the label. The lights are off. Oh. What is it, guys? That is not sodium. That's strontium. Yeah. Okay. Now let's go with this one. Okay, turn the lights on. Okay. This was actually lithium. Okay, lithium or strontium. This, I'll give you, kind of similar colors. Okay, that potassium. I'm sorry, that's sodium yellow. The old street lights, remember? Sodium vapor lamps, and it always just glowed yellow. Oh, you. Okay.
What's the colors? Okay, so we're gonna move the colors.
This overspray.
This is just
a second here.
move the colors. Let's see if I can get a place to plug this in, because it works better that
Here,
way.
I'll send you an extension cord.
Oh, I got this.
That one?
So you need the water hot?
Yeah, I do. So here, I'm gonna send you this one. Alan, you standing by there?
Okay. So,
Almost lost all our candles.
Oh, how are we doing down there?
One left.
Top two?
so, red, why these three colors? What's
Primary.
Yeah, the primary. What do you get when you put all these three together? You get white, so can you kill the lights? And should see a nice, this is white paper, right? And it looks white paper, right? Interesting, you look at the pins. You see the different color of the pins? And you're grinning because the shadows are looking kind of different, aren't they? Yeah, what color shadows do you see? Actually, that's not a red shadow, is it? That's kind of a pinkish color. It's called magenta. Yeah,
You can see it on the whiteboard behind him too.
and probably can.
Oh, wow.
Yeah, the shadow of the board too. Because the pinkish one is the magenta. Yeah, cyan is the bluish one. You can see yellow off to here. Okay, now, why those colors? Well, if you just have red and blue going, you get a black shadow, you get a red shadow, you get a blue shadow, don't you? Yeah, and so you can see they got all three going. You got a black shadow, but you got this blue. What's happening here is being blocked. Does that shadow come? That's easy to see on the pins. It also does interesting things to. I just unscrew this and we just use the red. Now look at the colors of the pins. There's your eye. Yeah. There are colors of light and there's colors of paint. There's light and there's pigments. And sometimes we just say colors. But the light is additive. The more colors of light I add, the brighter and whiter things get. The more colors of paint you add together, the darker and blacker it gets.
So does that mean I need to put more light into my laundry? I can put a light bulb in the washer. I'm good with that.
Right. Okay. Next.
Next. Lights.
Lights. We'll do that.
Okay.
That's just kind of cool off.
You ever watch TV
No,
and see
never.
commercials for the stupidest products you can imagine? Okay, the Snuggie comes to mind. And then you go into Bed Bath & Beyond, and you see this whole rack with a sign at the top that says, "As seen on TV." Well, as seen on The Big Bang Theory. At one point, Sheldon thought it important to get even with Kripke.
Oh.
Because Kripke pumped his office full of helium while he was doing a live radio broadcast. He decided to leave a present for Kripke in his lab. That present goes under the name of elephant toothpaste. Now, I'm going to repeat something that we did today already, but in a slightly different fashion. This is the hydrogen peroxide, the 35% variety, in its nice accordion bottle, so the bottle does not explode. I'm going to pour at an angle, hoping not to get any onto my fingers.
Otherwise, his fingers will be as white as his jacket.
That's right. Okay. Put in 100 mils of that stuff. That's like a $12 pour. You realize that? That's more than a Johnny Walker Blue. A few of you get that joke. couple of drops of the soap in here. This is Dawn Ultra Special Care. Tough on grease, easy on hands. And this is some food coloring. This does not actually look like your normal little short container of the food coloring stuff. Yeah, because I'm cheap. This is the plain wrap. Okay, this is the store brand food coloring. A few drops of that. Picked blue because UCLA beat USC this year. Now, I am going to add that iodide catalyst. This time it is a saturated solution, and let that decompose. Okay, and this is what Sheldon did in the ceiling up above for a piece of
Similar results, I might add.
As seen on TV. And if I'm not mistaken, the president of the university was visiting the lab
Where's our principal?
when that happened. Not here. That's a nice mess. Now, who would like to tell me what that is? No. You have a trash can landing? There's one on the table. Don't you recognize the color? It's not brown. Say it again. It's iodine. The iodide was converted to iodine. Okay, and that's what you ended up with. This will stain my floor for the next few years. You just sit right now. You can take it away that way. You just put the can under
Here's another little, nothing really super, but it's, I don't know, interesting. Got my attention the first time I
It's
did
hot
this.
in the sink. It's hot
You've
still.
seen a double pan balance before? Probably never one used like this. I'm hanging the mass below it and still weighing it, so I cut it out. Reasonably balanced. It doesn't have to be perfect. And I'm going to put this down graduate cylinder with water in it. What's going to happen? The balance. Why, it doesn't balance anymore. There's buoyancy, isn't it? Now this still sinks, right? But there's still some buoyant force. Gee, wonder how much. Can you see? Can you see about how much that water level is starting? About 60 milliliters. And now what is it? 773. So that's like the volume of this mass, isn't it? And so it displaced that much water, about 13 milliliters of water, right? So working this backwards, and I can't see it. You got to rebalance it. I put this back. That's 10, right? Okay, now I got to go back to 20 and then move over 7, right? Something about like there. And now, yeah. Well, okay. But you see, it's getting close. I can't see the numbers, so yeah. And it's almost balanced. So, oh, look at that. I displaced 13 milliliters of water, and it changed the mass that the reading I get here by 13 grams. Because what's the density of water? 1 what? Gram per what? Cubic centimeter, aka milliliter. Right. So that's why. So we got a displacement now. Okay, moving on. Wait, there's more.
Act now. If you call in the next 5 minutes.
No extra charge. We'll bring you a beaker with blue water in it. And,
A 1995 value.
except now I'm going to find out where does this balance. I'm going to get it close. Nope. No, it's too much. That's not enough. Move the rider over. You should try doing this backwards sometime. Okay. All right, close enough. Now, what's going to happen when I put this in, but not let go? Let's put it down in here, into the water, and just hold it part way down in the water. It upsets the balance. Look at the Okay, a couple people asked are Archimedes and Newton. Okay, and Newton's third law. Yeah, what's Newton's third law say, really? Yeah. But that's the short version that gets you into trouble and doesn't explain very much. It's not about cause and effect. It's not, well, he hit me, so I had to hit him back, you know, action and reaction. It's not about that. It's, if I put this weight down the water, that weight's pushing on the water, isn't it? So obviously the water pushes back on the weight. But what else is the water pushing on? It's pushing on the beaker, isn't it? Oh, so yeah, so it's upsetting balance. So there's more to that. But anyway, I thought that was interesting. Okay.
All right. I thought he was going to be running through the streets naked, yelling "Eureka!"
That's the difference. That you did give me the goal first.
Oh, okay. This is a temperamental little thing, but I like it. This is a beaker. Okay. My seal is not great down there. This is a beaker of hot water, which I will not throw on.
Oh well. You put food coloring?
Yeah, I got some food coloring.
Oh, okay.
Okay. Some food coloring. I'll put that over here in the cold water. Okay. Now, stir it up just a little bit. Blue for cold. Should be able to remember that. Okay. 3, 2, 1. Cold water is denser than warm water. And water is at its densest at 4 degrees. The lake freezes from the top down, not the bottom up, which is why there exists, and I'm probably going to offend at least one person in here, if anybody's from the Midwest, the stupidest sport on the planet, ice fishing. These are guys who go out and cut a big hole in the ice with a saw.
Yeah, don't do it like
in a
that.
circle. And then they set up a hibachi so they can barbecue their lunch on the ice. Makes sense. Okay? Farm boy. So I just
They
think
build
that,
fires on the ice.
yeah. So warm water is less dense, goes up onto the top layer. Cold water, more dense, goes down onto the bottom. Okay, cool.
Let's volunteer. Volunteer.
This is a bowling ball.
Does anybody here have an overbite? Want to get it fixed?
The following demonstration is known as faith in physics if it works, face in physics if it doesn't. And basically, this is about Can you help him out for a minute? Yeah. And hold this. Yeah. Now back up.
Now, Alan, you want to stand very straight.
That was loud.
Drop it.
Just let go.
Walk off to the side. 1 year I had a volunteer who was so relieved he walked straight. Yes, it did come back as pendulums do, and it contacted him a little lower than his comes squeaky. So back to the theme of the spacecraft. They launched the spacecraft, and after that falls away, and the second falls away, and the third falls away. They're out there, and the rockets are done, and they're just coasting, right? You don't need to have the engines running for the spacecraft to keep moving. It's already got kinetic energy, and it's going to keep moving. Yes. It's going to keep on moving and moving and moving until it's given a reason not to move. It's called Newton's first law. That's why the astronauts refer to Newton being driving light stick. So there you are in this out in the dark. You bring scissors. So,
Rodrigo Lopez from Victor, please dial 4423. Rodrigo Lopez from Victor, dial 4423.
So, you got it. Earthquake happens, gas line broken, you know about that.
Oh, yeah.
You don't want to be turning on, lighting candles, the gas is broken.
Oh, yeah.
You want to light, the electricity's off, so you want to do something like a light stick. And then
You call that a light stick?
oh, Rodriguez, take Bill.
We've been testing that.
Check your midichlorians.
We can tell who lost the course. You thought I was just here as a sideshow, didn't you?
Luminal.
Oh, we're doing it.
Yeah. Out of order.
One of the things that we find when we look at things that are biological is that as we study outer space, we also study something about inner space. And one of the frontiers that is still being studied a great deal is the ocean. And we find when we get down the deep part of the ocean, we find some rather interesting organisms in the ocean. Some that glow in the dark, luminescent organisms that produce their own energy. And we've been talking here about energy and the production of energy. Light stick with its production of energy. How does an animal produce energy on its own that produces light for it? How do some of these organisms produce the light that they produce? What does a firefly do when it gets light? How does it do this? So we're going to do a little demonstration here today of some light producing processes. Oh, we're all set. Ready to go. Get up here safely.
You want, we can hand it up.
Not good. I have here two solutions, and I want you to watch closely this spiral that you see right here. Can't see a whole lot with these right now, but watch. That is the way we produce light. Now, all we've got to do is figure out how we can produce light in cool ways like this. And share all of our energy needs, right? I'd like to have a car that ran on production of energy like this instead of on gas. There you go.
So how much did that cost?
It might not be cheap.
Yeah.
But some interesting kinds of ideas about production of energy.
Time for a little contest, don't you think?
Yes.
So need some volunteer, and it's, okay. Come on up.
No.
Oh.
And see this opportunity. Now what I think is, once you climb up there, drop to the top, and race down.
Everybody be standing on the left.
And now hold on. The contest is you come down, catch it, drop it, and then, yeah.
Tall.
You figure out.
Cody, he's 3 times your age and twice as fast.
Okay, so we go in at the top. Okay, now. See? All in one. It's time to learn how to do it.
Enjoyed your session.
Now, since it's not a magic show, we'll do it like Penn and Teller, and we'll give it away before it starts. I have a balloon and a flask, right? Okay? And in the bottom of the flask is a rubber stopper. Now, when we used to do elementary outreach and try to do cool things for little kids, you'd give this to a little kid and have him blow up the balloon.
That's an interesting shade of red.
Yeah. Then the teacher comes up. Okay. Okay. Now, by opening up the flask, I'm allowing air to leave the flask, and I'm not pushing against a trapped volume of air. Okay? Now, pull this out, and it's gonna go like that. Let's try something a little bit different. Okay. Now, got it pretty full there. What I'm gonna do, I'm just gonna get myself a little bit of water here. I think this bottle's leaking. Yeah. Lenny, you want to get rid of that bottle? It's definitely leaking.
Pour it into the container that's on top.
Okay. I need to practice safe science. So few people get that joke. Okay. Water.
Water will run.
Okay. Now, how did I do it differently the second time? It covered the bottom, didn't it? Okay. And I could have left the air in there, you know, thought the water flow would have stayed that time. Okay. When I pull this out, I have the added weight of the water, don't I? That's helping keep it down there a little bit, isn't it? Now, if I was like most high school teachers, Jeannie be going home for a t-shirt right now, right? Okay, because you get the little kid look over, and you know, very subtly do it with your finger. Everything in magic is distraction, isn't it? Okay, while I take out my magic coin, and what are you all doing? Looking at my magic coin while I'm positioning my finger down here. Okay, it's all distraction. That's how you make it happen. Okay, Mr. Orson, I think? Oh, Benedict, okay.
Are you getting thirsty yet?
You said you've been about that?
Is that the torch?
I didn't take it.
Oh, there. Ah, gotcha. Spark tank gas. Oh, it does.
My favorite kind.
It is. It's really foamy.
We may have to.
It's warm.
You want me to do my thing while we wait for
Yeah.
everyone to
Yeah. Go
down?
ahead. While we set
That'd
this.
be good. So, we'll come back over here, and,
Fernando. How many late lab reports did I take from you yesterday and today?
Yeah. Well, you know, I've got a camera. Look at the string on the camera. Okay. Now, let me move the mat.
Right here. I got matches.
All right. Boom. Feel free to stand up and touch. No.
Oh, the force!
So you see the candle flame. What's going on with the candle? Oh, went out. Why is it doing that? What's the candle flame made out of?
Wood.
No, what is fire?
Plasma.
How do you see the light? Yeah, you got a bunch of ions of plasma, right? A bunch of ions. Makes sense, ions to be attracted or repelled from a big electric charge and help discharge that. You got like a wind coming off of there. And then, let's see if this works. I didn't test out this bulb. Oh, there we go. Can you see it flickering? All right, turn the back light on.
Touch it.
Lightsaber.
Anybody ever go out and see fireworks on the 4th of July? I tried to. They didn't go off this year.
Yeah, they did.
Not in San Diego.
It was just all at the same time.
I sat for 2.5 hours holding a good spot to see that. But the show didn't happen. So we got
Since
some
we
fireworks.
didn't get to see them this year, I brought my sparkler.
Now bring it to the surface landing.
Come on, put it out already.
You see what's happening up here at the top? I don't know how many of you saw that. Did you see it burning up here at the top?
Yeah.
Any idea why?
Oh, because this oxygen.
No, but thank you for playing. Who said electrolysis? Very good.
What's the result of electrolysis?
Hydrogen and oxygen.
And so what did you see burning?
No.
When I brought it up here into the bubbles. The hydrogen was burning there. We get the hydrogen burning out of here because we've got electrolysis going on down in here. Now, I have another question for you. Last time I checked, normally when you put something burning into a liquid containing water, which this does, it goes out. Why did it go out? Idea what the heck's going on?
It
What's
wasn't
required
burning
in order to
oxygen?
have a flame? What do you have to have? You gotta have fuel, we have that. You gotta have the spark, we have that. And you gotta have, where was it getting oxygen when I put it down in there? The electrolysis produces, it was generating its own oxygen in there enough to keep burning underwater. You ever wondered how they repair ships and other kinds of things? How do they go down and weld them under the water? If you ever watch some of these shows where they're showing how they go in and do some of the metal repairs underwater, the diver goes down, the next thing you see them doing the welding down there under the water. You do it with this kind of thing.
So what's the metal that's in that strip?
This has to contain something that can do that, doesn't it? Obviously, it wasn't quite the same as little fireworks, because if you've ever done sparklers and you throw them in a bucket of water, they go out. Any idea what might happen?
Alan said it.
Magnesium.
Magnesium. Magnesium can burn efficiently. It can change. It can break down the water into the oxygen and the hydrogen, and you can do actually keep it hot enough that you can actually do welding right under the water.
We used to have an assistant principal here who was also a fireman. Okay? Scott's smiling. He actually would come to this every year. And he got up, like, uh-oh. After this down, he goes, yeah, I'm in the fire department, Sierra Madre. We have a memo that tells us if a Porsche catches on fire, not to put it out, to hose down the ground around it. What are the very fancy wheels? Israel, where are you? No, they're not chrome.
Magnesium.
Magnesium.
Mags. You ever heard of the
Mag
term
wheels.
mag
Oh.
wheels?
And there's no point in hosing it down because that's going to burn even underwater.
Underwater. So put water on it, don't put it out. You have some special phones, or you just let it burn out.
Like the older 80s model cars.
For that reason, right. So apparently not anymore.
If I say thermos, I'm providing a commercial for the King Sealy Corporation.
And we don't wanna do that.
We don't want to do that. So I should be saying Dewar flask or vacuum flask. This is double wall. What's between the two walls? Nothing. Thank you. Okay.
As little as possible.
Lisa, where are you? Is Lisa here?
No, she had to go.
left? Everybody say thank you to Lisa. Lisa paid for the liquid nitrogen. Came out of her lab. And she gave us a full 10 liters. Tomorrow's gonna be fun.
Harry Potter.
That is not water.
That's liquid nitrogen.
Harry Potter.
It is just a degree or two colder.
Harry Potter.
Dude.
Spilled it all over the floor.
Freezing hot.
Harry Potter.
Now, hold on. This is boiling like mad, isn't it? Boiling does not mean hot. What does boiling mean? A liquid changing into a gas. Now, what's happening is that the Dewar flask is coming to temperature. It was very warm. And I probably poured it in a little too fast for complete safety, okay? But once it comes down and gets to the right temperature, getting equilibrium going, you can see this looks very much like boiling water, doesn't it? Okay, but it...
Don't drink it, don't put
Don't drink.
Don't try to cook in it.
Now, here's the thing. You need to understand something. Your mom did not pack your lunch right. How many of you had the Spider-Man lunchbox? Okay, yeah. With the thermos. And the thing is, Mom put the juice in the thermos and put it in your lunchbox. Wrong. The juice was always warm. Mom needs to put ice water in your thermos and let it sit for 5 minutes. Dump out the ice water and then put in the juice. Or if it's for hot tea, fill it with boiling water, get it to temperature, okay, and then dump out that water and put in the hot tea. It'll last 4 times as long.
You didn't realize it comes from a cooking show.
More Michael Simon.
A little biology combined with a little chemistry and physics.
Dude, it was already dead.
It's now being boiled.
Looks good, doesn't it?
Magic. It's porcelain.
Any of you ever had a frozen banana before?
Not all the way, not all the way.
You do not want to submerge a banana all the way. Not into this stuff.
Banana's full of water. How many put a Coke in the freezer? We lent a Dewar to a guy down at Garfield High School one year. He put the banana all the way in. He bought us a new Dewar. because the banana exploded while the principal was in the room watching him.
You gotta get some point for exploding banana.
That's it. No, I was getting love ready for you. I'll hold things.
You wanna lower that down a little bit more. Oh, yeah.
Okay. Nail, board, and foot.
Sometimes when I go out to my garage, because I'm not the best at keeping things where they belong, I can't find my hammer. And once in a while, you just have to make do with what you can find.
Is that called a senior moment?
No, that's what you had with the lightsaber.
I'm not the one that turned 65 this year. I think it looks done.
I think it's done.
It's done.
All
It's a
right.
well done.
Stick a fork in it and see if it.
Stick a nail in it, see if it's done.
Some days you just, as I said, make do with what you got. And I want this nail in this block of wood, so.
Doing good.
It's not done. Done on the outside.
Now, if we just had some ice cream and chocolate sauce, we could have a banana split.
Oh no.
Here's the roast banana. Somebody's dinner? No? Alright, I guess it's game time.
This is an old one, but it's been used a lot. You can still see the label, right? Okay. Okay, so.
Pen double performance guarantee. If any pen ball should fail before the logo wears off, Pen will replace it with 2 new balls. Grab one out of the store. They moved it.
What do you think?
He's the second one. He's going to get a hammer. Okay.
Whoa, that's better.
A little bit
I got the label.
cool.
That's a 2-for-1 sale.
That's cool. Literally cool. What's the temperature? Oh, you're gonna have another one?
Yeah, but I'm gonna do something different. It's about 77 Kelvin.
Yeah.
Yeah, it's pretty darn cool. Okay, now I'm gonna let that boil for a minute or two and do something else here.
You do see what it says on the balloon, right?
Chemistry is a gas, problematic. Now, if you're a 3-minute egg, this is a 1.5 minute rack.
2-minute rack.
I have a little dexterity. I'm just gonna set that there for a little bit. Now, get those gloves? Yeah.
What you need?
Actually, I think I'm gonna skip the gloves. What I'm gonna do is I'm just gonna take the balloon. I'd like you to pour some of the nitrogen into there. We used to have a very nice porcelain evaporating dish to do this in, but it got broken and nobody makes them that big anymore. That's pretty good.
Michael scale chemistry.
Not quite reaching. Okay, so pour some on top. Just dribble it. Just dribble some there.
Cold air. There you go. Look at the balloon change color.
Now, you have to be very, very quiet for the next part of this demonstration. That's good, that's good. Because what I want to do, believe it or not, is pull this balloon out and shake it. Now, look in here. Do you see it? There's liquid in there, huh? Now, you can't tell from this orange balloon, but that's blue. That's liquid oxygen. We have liquefied the oxygen, okay, that I was exhaling. And if you're thinking, wow, he's exhaling oxygen, you all are. Best athlete in this room. Francis Tran, where are you? Best athlete in this room. Your lungs are probably about 37% efficient when you're marathoning. Okay? You put out a lot of that oxygen. Now, ice chips. The moisture that was in my breath. Okay? Now, I am going to cool the volume of air that's in that flask. The molecules will slow down. They will not be pushing up as hard. The pressure is going down. The law of Gay-Lussac. The air outside is still pushing down on the egg. And what is happening? No, it is not getting sucked in. Science never sucks. Suck is a four-letter word. Now. Okay, I'm going to warm this up. You did this to me! Switch my hand. Let's see if we can expand that. Oh, there you go. There you go. Come on. Come on. One more good push.
Is that going to a neighbor?
It's an
Give it the breath line.
Oh man, this might have to be a C-section. You're almost there. Now, one time doing this in class, years and years ago in AP Chem. Well, here it gets doesn't work. So we figured, all right, we poured in some liquid nitrogen into the flask with the egg, inverted it, and the egg immediately got stuck in the neck. And then what did the liquid nitrogen do? It evaporated and created a large pressure. And we did a perfect parabola in the second row. Do you remember who I hit?
No, I don't.
Charlotte Wacker,
Oh.
who is now the chief coroner for the city of Honolulu. And I have this nightmare of her actually getting even with me someday. And doing some, she's a medical examiner. You know how we always make the joke of, don't get sick, because y'all aren't going to make good doctors? Her response to that was, no, go ahead. It's all right. Let them train bad doctors. It'll keep me in business. Okay. Now, all right. Let's get in here. I need some protective gloves.
Yeah, those are probably not gonna protect what you plan.
Well, the thing is, the reason this is so hard, Maria, you bought the smalls.
Just one size fits most.
One size.
One size fits small. You want to just use that here?
No, he's
All right.
careful.
The rubber gloves, you know.
Woo!
Lot of
Yowza!
protection.
We have hot chocolate tonight, sweetie. Woo! Okay. What I won't do for science. Now, Mr. Larson, could you mop that up for a second? I have to dispose of this, actually.
Yeah.
You left a lot of water in there. Okay. Tomorrow, I say we go for the center stairwell just about during casting period. Spill a little water down the stairs and we just dump this from the top. And we'll get someone to walk right out and yell, help me! At least they get that joke. Not just a bunch of flying monkeys. Okay. You like that? Grab yourself a set.
I know.
Okay.
Carbon dioxide, when placed in water. Oh, I'm sorry, it's Thursday. So, Shauna, you ready? A stream of carbon dioxide is bubbled through a solution of distilled water.
What? Wrong answer.
Carbonic acid is what?
Carbonic acid. So,
Notice ice sinking. If you see ice sinking, yeah, well, maybe.
Not really.
Carbonating your drink.
isn't this what chemistry was supposed to look like?
Yes.
Couldn't forget to put Very cool.
Before the other one.
Zone.
Take a deep breath. Breathe it away.
No, it's not smoke.
I had this in my hand to start with. I had a matchstick.
Oh, good, yeah. graduated UCLA. How did you know?
That's not gonna take up for a week.
There you go, UCLA.
I think to get kicked off.
Nice soothing sound over there, like water dripping down.
While he's setting this up, by the way, did any of you happen to notice what's happened to the candles?
They went out about half hour ago.
Yeah. They're gone.
Okay, catch that up.
Hey, you good? You got the smell?
Just let it go. Release.
Oh, he's gonna put bubbles in! George, you can see what he puts out. Awesome. We made a comment one time with that. We got charcoal. No, it was it was charcoal.
Now,
That.
what is it that you're actually seeing? It's not smoke. It's not water vapor. It's liquid water. It's liquid water that has condensed vapor from the vapor because it's so cold on dry ice. And that's your basic movie special effect. That's how you make a cloud. It's really that simple. Okay? A little hot, a little cold. Dry ice. Our house can be kind of fun on Halloween.
Dude, you can make a bomb out of that. You can get a plastic garden. And you put one of those in there. I thought you were saying something.
And what are we doing? We're doing exactly what we're trying to teach you to do. Experiment, right? Come up with a theory.
And test it out.
Test it out. What are the 4 things you need for an explosion? Fuel. Ignition. Oxygen. Closed container.
So we got the explosion the first time because we had all those elements in place, didn't we? Why did we not get an explosion the second time?
Fuel.
Oh, the fuel's in there.
There's fuel.
But the oxygen, because we exploded the fuel, right? So we burned the oxygen along with the fuel, and kept back on pretty quickly. So what am I trying to do by doing this, installing, waving it around? Is I'm trying to get a gas exchange between in and out. Okay.
Ooh, in and out.
You're getting hungry, are you? Dinner time? Okay. So
Let's get a burger.
yeah. So eventually, no, but not right now.
Yeah.
Sometimes it takes a while.
Puts enough liquid oxygen in there.
Yeah. I was
There you
thinking,
go.
But where's that balloon?
I wouldn't do that. Hold on.
Do you remember where that was?
In the liquid engine.
But what did I do?
Right now.
I let it warm up. Okay, come back to room temperature. Now, can I let the flour rest? No.
Peace.
Okay, so it's experiment, right? It's try and come up with an idea for why it's working or not working. Now, time to go a little different with it. Where's that bottle of alcohol?
You and your own.
Recycling.
Repurposing.
No, I don't think the egg will fit. I don't think the egg will work.
Yeah. It worked for me. That's like a first. Yeah. That's why I'm surprised.
I got yours. No, I got wet. This one got wet. Yeah, the sparkler on it got wet. Okay, you know what? I'm pissed. I'm angry. I'm mad. Mine didn't work.
Those stinky.
Forget micro scale.
Michael scale.
We're going micro scale. is not good because it's going to get the light.
When they installed, the day after they installed these, we came in and saw them up there and we said,
Nope.
not a good place.
And they just
Said,
kept,
okay, we'll move them.
and then they just kept saying this phrase, change order. And I didn't get that.
I don't think that's what it means in construction.
Now, I want you to be very quiet. What happened? Air did not escape. No. Methanol escaped. Alcohol. Because what I'm doing here is I'm vaporizing it. Okay? And it's building up pressure. Alan, are you over there by the... Okay.
Yeah, tell them in advance.
This is, it's a little loud, but doesn't hurt your ears. It's something you want to look at. We're going to turn the lights off.
And you want to listen to. So I know people yell a lot, but
Yeah,
after the first
silence.
one, listen to.
Just listen to this one. Are you ready, sir?
Almost.
Okay. Alan, lights off. Incoming!
Oh, yeah.
Lights.
Daniel.
Sorry, take that. Have some potato chips, please.
Yes.
I used it with rubbing alcohol. In a glass of milk. And you get a match.
Elton, you are so wrong, it's not funny. I bought this in 1992.
It's my 20th year.
Is it stale?
Well aged.
Okay. Oh, you brought the new one. You haven't taken that out yet. I meant the red one. You're gonna need a wrench to get the red one. That one's not open yet. Now, this will be about the same volume, okay? But it's gonna be a very different effect. We're gonna sit this down, we're gonna light it, and it's gonna burn. The gas that's coming out, which will be hydrogen gas, will be burning with oxygen it finds out here. And you'll see kind of a pretty little blue flame. Okay? Now, while that's happening, this hole in the bottom, yeah, now that's Michael scale. Air will be going in. And at one point, we will get a mixture in here of 2 parts hydrogen to 1 part oxygen. Okay? Kaboom. It will be loud. It will hit the ceiling. Okay? But I'm going to tell you to be silent. Because you're going to know when it goes off. You don't have to cover your ears. It'll be loud. You cover your ears later. But you will hear it hissing. When it stops hissing, that's not good. Yeah, get over to the lights, Alan. Give me a second to get this thing balanced. Lights. Now you can see the flame. Don't photo, it won't work. It's a nice try, but it just won't work. Listen for the sound. Green. All is safe. All systems operational. This is a balloon filled with helium. We're going to pop this balloon. It will not be loud. It will just be the sound of a balloon popping. And out will come a whole bunch of helium, which does not support combustion. Watch. Alan, C2, please. Turn off the lights.
Stop waving your balloon.
Woo!
Killed it. My beautiful balloon. Yellow.
Yellow. What does yellow mean? Do not say accelerate. Caution. Wow. Do you see the difference? It's really flying up, isn't it? Yeah, the molar mass of this gas is exactly half of what helium's molar mass is. I have a balloon full of hydrogen. It will be loud. It's going to make a beautiful fireball. You want to watch it because it's going to pull the oxygen in from the outside, and you'll see it burn that way. Right?
Yeah.
Okay. Alan, C2. Does anybody wear a hearing aid?
Not yet.
Seriously.
Does anybody have a heart condition? Here's what's going to happen. For us